So let's get started. Today we are going to start new chapter, chapter 10. This chapter is going to be about moments of inertia. So what does it mean by moment of inertia? Moment of inertia, it's very important property, help us to understand how much moment any section can take. So it's very important property. It's indicator for the capacity of any member to take the moment. Later on in advanced courses, we are going to use the moments of inertia a lot. So today we need to learn how to determine the moment of inertia for the any section. So the definition of the moments of inertia for area, we said that it's frequently used in formulas related to the strength and stability of structural members or mechanical elements. Like I mentioned, it's very important property, help us to evaluate the capacity of a certain structural member to take the moment. And in the previous chapters, we'll learn how to determine the moment about a certain point. And all of this process, it's very important to design your building or your mechanical elements or your structural elements. So what is the definition of the moments of inertia? The moment of inertia for an area, so if I'm going to have a certain area and it's required to determine the moment of inertia, we are going to take the integral of the second moment of area about an axis in question. For example, here we have axis x and we have axis y, and here we have arbitrary area. So here we have an area and we have axis x and axis y, and it's required to determine the moment of inertia for that area, let's say about that axis here, x-axis. In this case, I'm going to integrate. I'm going to use integration for the differential area, and I'm going to take the moment for that differential area about the axis x, and it's going to take the moment twice. So if I'm gonna determine the differential moment of inertia about x, is gonna be y squared dA. dA times the perpendicular distance here. Here is the first moment. Multiply again by y, then it's the second moment of area. So also we have another name for the moment of inertia. Sometimes we are going to call it the second moment of area, because we are going to take the moment twice for that area. So we are going to take a differential area. We are gonna get the moment about that axis for the first time by multiply by y, and then the moment for the second time by multiplying by y again. So now the differential moment of inertia about the x-axis is going to equal y squared, the distance here, times dA, the differential area. Now, if I'm going to get the whole moment of inertia, I need to integrate. So if I'm going to integrate this, then I'm going to get Ix. Similarly, if I want to get the moment of inertia about the y-axis here, then the differential area is going to be multiplied by the distance x for the first moment, and for the second moment, I'm going to multiply again by x. So the differential moment of inertia about y-axis is going to be x squared dA. If I want to get the entire moment of inertia, I need to integrate that part. So the moment of inertia about the x-axis for that area here is going to be the integration of y squared dA. Similarly, for the moment of inertia about the y for that area is going to be the integration of x squared, this distance, times the dA. Also, we could take the moment about axis r here. So if I'm going to have axis r here, then the moment about the point O, we call this the polar moment, and this one is very important when we are going to deal with the torsion. Later on, when we are going to deal with the torsional stresses, the polar moment of inertia is very important. And this one is going to be the integration of r squared, this one squared, dA. And r squared is actually x squared plus y squared. So we can say that the polar moment of inertia is the moment about x, the moment of inertia about x plus the moment of inertia about y. So Ix is the moment of inertia about the x-axis. Iy represent the moment of inertia about the y-axis. And the J, initial J, is represent this one here, represent the polar moment of inertia. Again, moment of inertia is very important property. You are going to use it in your advanced courses, especially in the next course, which is strength of material. You are going to determine the moment of inertia for the certain sections, because the capacity of the moment for that structural member depends on the value of the moment of inertia. Also, we have a very important theorem. It's called parallel axis theorem for an area. This theorem is very important, especially when we are going to deal with the composite sections. Remember, we talked about the composite section in the previous chapter, the center of gravity. We say that we use composite sections a lot in engineering. And if I'm going to have composite section, that means it consists of many common shape or parts. So that theorem is going to help us to determine the moment of inertia for composite parts. Then it's very important to understand the principle of that theorem. So again, assume here I have a random area A, and I have a random axis x and y. Here I have another reference axis x hat and y hat here and here. They are located at the center of gravity. Last time we discussed the concept of the center of gravity. So we have a random x and y, and here we have x and y located at the center of gravity. See here, refer to the center of the gravity. So I have an area, and I'm going to assume this point here is the center of gravity. I'm going to put the reference here, but I'm going to call this x hat and y hat. So now I can determine the moment of inertia for that area with respect with x hat and y hat. So the moment of inertia for x hat here is going to be the integration of y hat squared dA. Similarly, for the y is going to be the integration of x hat squared dA. Then I'm going to give a name for or a different symbol for the moment of inertia about x hat. I'm going to call it x dash ix dash here, which means that the moment of inertia about axis x here, which pass through the centroid. So I'm gonna put a bar here, ix bar. It means the moment of inertia for axis that go through the or pass through the center of gravity. Similarly, the moment of inertia about y hat here, we are going to call it iy bar, which means that the moment of inertia about axis y that pass through the center of gravity. So now I know ix bar and iy bar. I know the moment of inertia about this axis and that axis. Now I need to know the moment of inertia for that area about axis here. It could be any axis, it could be here or it could be there. So in this theorem, we are going to determine the moment of inertia about axis, any axis, which is parallel to this axis. So the first condition, this axis should be parallel to that axis here. So I need to determine the moment of inertia about x depends on x hat. So in this case, the theorem says the moment of inertia about x is going to equal the moment of inertia here about the centroid plus the area times dy squared. So dy squared, the dy represent the perpendicular distance between the x hat and the new x. Dy here is the difference between the axes. Similarly, I can determine the moment of inertia about y with respect to y hat. So if I do know the moment of inertia about y hat using the parallel axis theorem, I'll be able to know the moment of inertia about y. So the moment of inertia about y is going to be the moment of inertia about the y axis that pass through the centroid plus the area plus the difference in x. So dx here is the difference between the that axis and that axis. Okay. Also, I can determine the polar moment of inertia using the same concept. So the polar moment here is going to be the polar moment about the centroid plus a d squared. D here is the difference between the polar moment and the polar moment about the centroid. So now we have two concepts. I have the first concept here, how to determine the moment of inertia for a certain area about a certain axis. And here, the parallel axis theorem, we are going to take advantage of the moment of inertia about the centroid, and we are going to determine the moment of inertia about any axis using the moment of inertia about the centroid. So let's see an example so that we can connect all these concepts together. So in example 1 here, it's required to determine the moment of inertia. So here we have a rectangle area, like you can see here. We have that dimension is b, and that dimension is h. But we need to know the axis. So you want to determine the moment of inertia, but about which axis? He said that about the centroidal x hat axis. So about that axis here. So we have axis there, and we have axis here. We call this centroidal axis because that axis pass through the centroid of the area. So we are going to call it the centroidal axis. So first, I need to determine the moment of inertia about x hat. Then we need to determine the moment of inertia about the x b axis. So here we have axis which is parallel to that axis. So in that case, since we already in part A determined the moment of inertia about x hat, we are going to use the parallel axis theorem in order to determine the moment of inertia about this new axis. Also, we need to determine the polar moment of inertia for the centroid. In order to do that, I need to know the moment of inertia about x hat and y hat. So let's start with the first part. In the first part, we need to develop differential element for integration. So here we are going to put, or we are going to choose differential element. It could be at any distance. Could be here or there or there. So at a random distance, we are gonna call it y hat here. So at y hat, we have a random distance, and here we have differential area. If this one is y hat, it means the thickness of the differential area is dyx, and the width of the differential area is going to be b, since this one is b over 2 and this one is b over 2. So I have a differential area. The differential area is b times dy hat, like you can see here. Then, like we'll learn from from this lecture, the moment of inertia about this axis is going to be the second moment of area. So I have area dy. I'm going to take the moment twice. The first time the moment is going to be multiplied by y, and the second time I'm going to multiply by y again. So I'm going to have d hat squared dA, and in order to get the entire moment of inertia, I need to integrate the whole area. And the integration limit here is very important. You need to take care about it. Your reference is here, and you need to take the moment of inertia for this part and that part. In that case, I'm going to integrate from here to here. If this one is a reference, that means this direction is going to be minus and this direction is going to be positive. So I'm going to integrate from minus h over 2 to positive h over 2. So the integration limits is important here. And instead of dA, I'm going to put b dy hat. So now everything is good, because I have y and I have dy, and the value of b is constant. I can't put this out since the value of b is constant. So now I'm ready to integrate. I'm going to integrate this one, and I'm going to substitute the integration limits. If I'm going to do that, the answer came out to be 1 over 12 b h cubed, like you can see here. So the moment of inertia for a rectangle about the axis pass through the centroid is going to be 1 over 12 bh cubed. And I can apply that formula for any type of rectangle. So this formula here, it could be used for any type of rectangle. So in the exam or in the quizzes, you should be provided a table that show these properties later on when we are going to deal with the composite parts. So here is the first part only. In the second part, we need to determine the moment of inertia about this axis. Now I know the moment of inertia about this axis, and it's required to determine the moment of inertia for this axis. In this case, I'm going to use the parallel axis theorem. I'm going to take advantage of knowing the value of the moment of inertia at that axis here. So in part 2, I'm going to use the parallel axis theorem, the moment about that axis xb is going to equal the moment of inertia about the centroid plus the area times dy. dy squared. dy represents the difference between the two axes. And the difference between the two axes here is h over 2. And the area, we know the area is b times h. What about ax bar? Ax bar is here. Is the moment of inertia about the axis or centroidal axis. So I know this value from here. The area is bh, and the difference is h over 2 squared. I can determine or simplify this formula. The answer came out to be 1 over 3 ph cubed. So now I determine the moment of inertia about the centroidal axis and about axis which is located here. The third part, we need to determine the polar moment of inertia. In order to determine the polar moment of inertia, we say that the polar moment of inertia is going to be the moment about x, the moment of inertia about x squared plus the moment about moment of inertia about y squared. So now I know the moment of inertia about the centroidal axis x. Similarly, I can evaluate the moment of inertia about y hat here. So the only thing that is going to change, here we have h cubed. When I'm going to determine the moment about the moment of inertia about y here, I'm going to have the same answer, except that b is going to be cubed and h is going to be only 1h. So the moment of inertia about this axis is going to be like that, similar to this one. The only difference is the cubed part. Here, h is going to be cubed, and here p is going to be cubed. And the polar moment is going to be, here we need to determine the polar moment about the centroidal. So it's going to be x, the moment of inertia about x, and the moment of inertia about y. And here is the answer. The polar moment of inertia is very important when we are going to deal with the torsional moment. Later on, we are going to deal with something called torsional moment. And in order to know the capacity of the torsional moment, it's very important to evaluate the value of the polar moment of inertia. So do you have any question up to this point here? See example 2. In example 2, we have a triangular area. We have the width and the height here. And it's required to determine the moment of inertia. First, we need to determine the moment of inertia about x-axis here. And then we need to determine the moment of inertia about the centroidal axis x. So this time, you want to determine the moment of inertia about x first, and then we need to determine the moment of inertia about the centroidal x. So let's see how that's going to take place. First, we need to develop differential area at a random distance. We need to take the moment about x here. So we are going to take differential element dA at arbitrary distance y hat. So the width here is going to be, or the height here is going to be dy hat, and the distance here is x. X is going to change a lot. So x is variable. It's not constant here. So I need to express the value of x in terms of dy. So in the first part, we need to develop differential element because we need to integrate that differential element. And here it's located at arbitrary position, y hat. Then the area of that element here, dA, is going to be x times dy dash. Again, remember when we were talking about the center of gravity, we express the value of x in terms of y. So I'm going to use the similarity between this triangle and that triangle. This triangle and that triangle. If I'm going to do that, the value of x is going to be b over h times h minus y hat times dA. So now we have expression for dA. We have only one variable, which is y dash, y hat. So now we are going to determine the moment of inertia. We are going to multiply that area by the distance for the first time and for the second time. So the moment of inertia about x here, or that axis, is going to be y dash square dA. Instead of dA, we are going to put this. Then the integration limit is, since the reference, we took the reference from here, we are going to integrate the whole area. So it's going to start from 0 to h. Again, the integration limit is very important. Here, x is not dash because should be without bar. X here is not without bar here. So now, if I'm going to evaluate this integration, the integration came out to be 1 over 12 bh cubed. But about which axis? About this axis. Now, in the second part, we need to know the moment of inertia about x hat, about the centroidal axis. And we are going to take advantage from knowing the moment of inertia about this axis. So remember, in the parallel axis theorem, we say that the moment of inertia about any axis is going to be the moment of inertia about the centroidal axis plus the area plus the difference squared, the difference between this axis and that axis. And in that problem, the difference is going to be h over 3, because we know the location of the center of gravity. According to the center of gravity, the difference here is going to be h over 3. So what we want here, we want ax bar. So we want ax bar. What we evaluate here is axb. So here is a mistake. This value is ixb. You should put ixb. Now we want that value. In order to get that value, is going to be ixb minus a dy squared. So ixb, we know the value from here. The area, we know the area, half times the base times the height. And dy, we know dy is the difference between the two axes, which is h over 3. So we know this from there. And the area, we know the area. And the difference is h over 3. The answer came out to be 1 over 36 bh cubed. So now we determine the moment of inertia about the centroidal axis x here. Like you can see here, we have the centroidal location and the moment of inertia for the most common engineering shapes. For rectangular area, here is the area, and here is the center of gravity, or the centroid. Here, if I'm going to evaluate the moment of inertia about x axis and y axis, here is the formulas. Similarly, for the triangular area, and for the circular area, and for the semicircular area. Those are very important because when we are going to deal with the composite sections, we need to use the formulas for the common engineering shapes. Okay, so we are going to talk about the moment of inertia for composite areas. And the composite areas consist of simpler parts, like those one here. So we need to take advantage of the moment of inertia for the common shape in order to determine the moment of inertia for composites part. Okay, so I'm going to stop here.